Hi, this is Brandon Baines in the Math Department at Lipscomb University, here to talk with you today about applications involving linear functions. In this presentation, you'll learn how to interpret slope in applied settings, how to interpret intercepts in applied settings, and how to model real-world scenarios using linear functions. Here's an example to get us started. A tank filled with 1,000 gallons of water is draining at a rate of 10 gallons per minute. How many gallons are in the tank after 10 minutes of draining? How many gallons are in the tank after 50 minutes of draining? And can this scenario be modeled using a linear function? Well, after 10 minutes of draining, the tank has drained 100 gallons since it drains 10 gallons per minute. So there are 900 gallons left in the tank. After 50 minutes of draining, the tank has drained 500 gallons. So there are 500 gallons left in the tank. Since the rate of change of the water in the tank is always a decrease of 10 gallons per minute, we have a linear relationship. So yes, the scenario here can be modeled with a linear function because it represents the aspect of slope using this decrease of 10 gallons per minute. We continue to think about this scenario. We'll attempt to write the equation of this linear function that will model the amount of water remaining in the tank after X minutes of draining. So keep in mind that the equation of a linear function follows the form f of x equals mx plus b, where m is the slope and b is the y-intercept. So since the water is draining at a rate of 10 gallons per minute, we will have a slope of negative 10, as we mentioned before. And we could also use an XY table to determine this slope. The y-intercept is the point on the graph where the x value is 0, or in applied settings, this might be interpreted as the initial amount. And in this case, when x is 0, we would have 1,000 gallons of water in the tank. That's our starting value. So our y-intercept here is 1,000, or the order pair 0, 1,000. So our linear function then is the function f of x equals negative 10x plus 1,000. We'll find the x-intercept of this linear function. Again, we find the x-intercept by letting y equal 0. And when we do that and solve for x, we find that the x-intercept is 100. And so the x-intercept is the order pair 100, 0. So what is the interpretation of this x-intercept, this ordered pair 100, 0 in this context? And in this context, then, it means that after 100 minutes, the tank is empty. It has no more, no gallons of water left. So let's review. Scenarios modeled by linear functions must have a constant rate of change. The constant rate of change, like the draining of 10 gallons per minute in our initial example, is the slope. And that is really a key aspect of linear functions. That is that the slope represents a constant rate of change in applied scenarios. So if we're talking about setting your treadmill to go at 5 miles per hour, then that represents a linear function because the rate is constant. If we set the cruise control in our car, that's a constant rate of change of 60 miles per hour or whatever we set the cruise control to. The y-intercept tells us the value of y when x is 0. And so in a lot of our applied settings, again, this is often the starting value sometimes called the initial amount, depending on the scenario. But the y-intercept is often an important interpretive point for us in applied settings. The x-intercept, it tells us the value of x when y is 0. And so in applied setting, this is when the quantity represented by the y variable is 0. So a lot of times this would be, if y is representing a height, it would be when the height is 0. So we might have an object in flight, and we want to talk about the height above the ground. So that could be when the object lands on the ground.